So let's go ahead and discuss some basic derivatives with matrices and vectors. So we want to start in the simplest case by thinking about the following equation. We'll let the vector y be equal to the matrix multiplication of A, which is a matrix, by a vector beta here. And let's actually go ahead and denote. Let's take this one more time. Okay, so let's investigate some simple cases of derivatives of matrices and vectors. So let's begin by thinking about a really simple situation where we've got some outcome vector y, which is equal to the multiplication of the matrix A by the vector x. And we'll give the dimensions of these things. So we'll stipulate that A is an n by k matrix, x is a vector in k-dimensional space, and then this of course means that our outcome vector y is an n-dimensional space. It's an n by 1 vector, and you can briefly check a couple of conditions here for matrices. So for matrix multiplication to be defined, these two items here have to be the same, and they are, and then this will give the dimensions of the output, and it does. So we can now go ahead and think about what the derivative will be here, and in particular what we want to find the derivative of y with respect to, in this case, x. So that's what we're after. And we can take this in a couple of different ways. Maybe the nicest way to think about it is that this turns out to be really, really intuitive. And so what we can say is something like this. So let's come back to our original setup here. What if we simply wanted to say, well, what if I just write out the matrix multiplication? And I prefer to write out matrix multiplication using what's known as the linear combination approach. So if you're like me, you like thinking about matrix multiplication in the following way. We say that any old vector x, and let's say the vector x is equal to 2, 1, is basically equal to going over 2 up 1. That's a simple way to describe it. So we might draw that vector here. But what does it really mean to go over 2 up 1, right? And if we think about that, we actually need to specify we're going over 2 things, but what are those things, and going up 1 thing, and what is that thing? And we really need to start thinking about also the direction. So we're going over some magnitude, and it's a magnitude in some direction, and we're going over or up some magnitude, and it's also some direction as well. And so implicitly, when we say go over 2 up 1, we actually have in mind go over exactly in the direction 1, 0. And then go up in the direction 0, 1. And then also do this basically by some magnitude. And that magnitude is also contained in what these vectors are. In other words, we could select, say, the vector 3, 0. And then we would say, instead of, or let's say 4, 0 to make the math easier, instead of saying go over 2, we would say go over a half step, right? And so implicitly, when we say go over 2 up 1, and we're indicating this specific vector, we have in mind a certain set of basis vectors, and we have in mind the standard basis vectors, which are these two here. This is E1 and E2. And what you can do when you think about matrix multiplication is, at least one way of thinking about it, is you're actually replacing those basis vectors, I'll keep the red pen actually, with arbitrary vectors. So note that we can actually define matrix multiplication sort of with 2 properties, or with 2 desiderata. The first one is that we should be able to think about all vectors as being represented in the same way. So for example, you can see here I've represented this column vector here, or this vector here, as a column vector. This vector here is a column vector, and this vector here is also a column vector. And so it's a desirable property of any kind of mathematical notation system that we should be able to write, objects that have the same basic proportions or kind of dimensions in the same way. So we don't want to, say, have to keep track of the fact that sometimes we mean 0, 1, sometimes we mean this to be a column vector, or a vector in this space. So actually, if you think about it in the way that we're currently thinking about these things, this actually represents two different vectors effectively, and it represents the vector 0 and the vector 1 implicitly sort of on the real number line. We don't want to have to stop and think, okay, well, does that actually represent something fundamentally different here? So that's a desirable property of the system. Secondly, we want it to be the case that if we write out these two vectors here in a matrix, and note that this is also the identity matrix in 2 dimensions. Secondly, we want it to be the case that when we multiply our given vector by this, we should get back that vector when we put in the standard basis vectors that we are assuming when we say that 2, 1 means go over 2 up 1. So that means that the matrix multiplication should be defined as follows. It should be defined as saying it goes over 2 in the direction of the first vector, and then we add to it. That's what it means to go up, or to do one thing first and the other. Then we add to it this here. And note that when we do this, we do get back the vector that we had, right? So what we don't want is a system where we're saying something, and this is oftentimes something that people want. Initially, they might say something like, okay, well, what I'd really like is something like this. I'd like to write a vector like this and then say that matrix multiplication means this, and I just, match these things here or something like that. But there's a number of problems with this system. I'll just mention one, which is that it requires us to write objects that are fundamentally the same, such as the 2 basis vectors and then the vector we actually have, in different ways. So we'll cross this through because this is bad. So then what does matrix multiplication actually mean? Well, what it means, for instance, is if we have a new set of basis vectors, and let's copy this down and give ourselves enough space here. And if we have a new set of basis vectors, let's say, I don't know, maybe 2, 3, and then 1, -2, something like that. So we would write those in like this. Now what we're doing is saying basically orient yourself so that these are your new 2 fundamental directions, but then do the same thing. Go 2 in the direction and with the implied magnitude of the first vector, basically use that as your fundamental step, and then go 1 in the direction of our next fundamental step. So we can do that now. So we would get 4, 6 here. So we'll come over here and then up here, and we'll do basically this, something like this. Sorry, that's a little bit off. So this equals 2 times, and then go 1 in the opposite, in the other direction as well, which is just down here. And then we say basically place these tip to tail. And then what we'll see is that we'll get back from that vector, of course, following. Oops. Let's write this out. So we get 5, 4 back. Pardon me. And so that's a way to understand matrix multiplication. So we can now go ahead and kind of look at what that looks like. Okay, so note here that if we think about, all right, how do we come up with the number of rows here? Well, if we come down here, we can see the x1 is constant here, so it's not changing in all these rows, and the size of the row is given by, the size of the rows, or the number of rows is given by n. And then if we come here, so if we look across the rows like this, note that the x in this case is also changing, but the number of rows, oh sorry, notice the mistake here, this should be yn, pardon me. The number of, sorry, the y is constant, but the subscript associated with the x is changing, so this is an n by k matrix. And what that means then is, again, if we think about taking our linear combination, so we put in a little x1 here plus x2 here, like this, this is telling us that if we multiply x1 by the derivative of y1 with respect to x1, y2 with respect to x2, or 1, and then we multiply here x2 by the derivative of y1 with respect to x2, and so on, up to xk, you can see that this derivative matrix is really nice because it allows us to go ahead and actually multiply, so we could do that linear approximation by the original vector. It could be the case, however, that we would use the transpose of this thing, and if we did that, you would have, I'm not going to write this out because it would be tedious, you would have a k by n matrix, and that cannot be multiplied by, I don't know exactly how to write cannot be multiplied by, let's just do this, cannot be multiplied by a vector of dimensions k by 1 because these things don't agree. So that's one reason to prefer the numerator approach. But again, people should spell out why they prefer it as opposed to just sort of saying take it on faith because that leads to lack of learning in the long run. Okay, so that would be our derivative. And then if we think about it, how do we fill out this matrix here? Well, the derivative of yi with respect to xj, so we came down here, this is the derivative of y1 with respect to x1. We don't need to write that in because it's written down there. This right here is the derivative of y2 with respect to x1. So we varied this index here to 2, and we kept the j. And you might just notice that this right here is just another way of saying also for some indices I and j, I'll write this here. This is just the matrix A, where I equals row index and j equals column index. And so ultimately our answer to the question then is that the derivative of this thing, this derivative of y with respect to x, is just going to be the matrix A. So we can write that up here. And that's our first kind of important derivative property of matrix calculus. So now we need to proceed to the task of finding the derivative of a so-called quadratic form. So let's define that quadratic form as follows. We'll write P is equal to X transpose times the matrix A times X. And we're going to note that in this particular case, note that this is only defined if we have certain restrictions on the size of the vectors here. So this is a vector in 1 by k. This is a vector in n by k just generically. And this is a vector in k by 1. Now note that for this to be defined, these two things have to be the same, and thus it needs to be the case that k and n are the same size. So like this. And let's write out, first of all, we'll fix this here, what this would look like. So note that this is now, we can go ahead and fill these in here. And there's another way to see that too, of course, which is that x transpose and x need to have basically transposed dimensions. So it doesn't make sense to say that k and n can't be the same. So let's write out what this would look like. And we'll see later on down the road why this is called a quadratic form. So what is this going to look like? Well, we've got here this vector x1, x2, xn. Here we've got a1, 1, a2, 1, an1, a1, 2, a2, 2, an2, and finally let's always do this. Slide this over. This is a1n, a2n, ann, and then finally this is x1, x2, xn. And we can think about how this would look in practice by saying, okay, well, how would we actually go about computing this monster? Well, we would start by, or at least one way to do it, there's many ways. We could start by taking linear combinations of the rows of A and the columns of X transpose. So what would that look like? Well, that would look like this. We would say we start by taking this dot product here. And then we can do this in a couple of ways. Let's actually finish the matrix multiplication here. So we'll pack these into a vector, which we'll call W transpose. And this will equal the dot of here, x1, sorry, not x1, just x, dotted with a1 as a vector. And note that a dot product requires the vectors to have the same dimension. So it is the case, I guess I should say that this goes without saying, but X transpose dotted with, or in this case, matrix multiplied by A1 is equal to X dotted with A1. That's just a fact about matrix multiplication I should mention in case you don't know that. Okay, so then we do the same thing here. We take this and that gets packed into this here. And then finally we come down here and that ends up here. And I'm not always going to write out the vector hats on the vectors when it's obvious because it's a little bit space consuming. So here I'm writing the vector hat on the A's because it's maybe not obvious since A is a matrix, that here we're just considering it in its vector components. So we would do that first, and then what we would do is take all the elements of that and multiply it by x. And so what that equals is the following. Oops. Sorry, I'm having a little trouble here with the computer. Well, I mean, it is a computer, the iPad though. Okay, and then we have here x1, x2. And so we can think about now replacing these terms inside this row vector with just w's. So we'll say that those are the same thing. And then what this means, of course, is then we're going to take the dot product. And so one thing to note, first of all, is that we're going to get a scalar output. And you can see that by thinking about the fact that WT is going to be a vector in one by n. And so that means WT x has to yield a scalar product. These match, and then these are the dimensions of our output. So P is a member of, if you want to think about it this way, it's a little silly, but P is a member of the 1 by 1 matrix space, or it's a member of the reals. Okay, cool. So that's a kind of picture of what this actually is going to look like. But let's go ahead and think about what we're actually after here. So what we're after is we want to find the derivative of this scalar product with respect to x. So we'll write that like this. So it's the derivative of this scalar product, and I'm going to write here the vector x explicitly. So from before, we remember that we like to write derivatives with the so-called numerator layout, or in other words, the way I like to think about it is sort of the linear approximation layout, which means that the derivative should be written in a way so that it could take, write the derivative so that such that it could take a vector x as an input. So of course then that would mean that this should be a vector of a vector derivative basically in dimensions 1 by n. So what this will ultimately look like, let's see here. This is going to be a member of the reals 1 by n. So we're after basically that vector of partial derivatives. So let's go ahead then and think about how we could do this efficiently. And actually the method we're going to use is not necessarily the most efficient, but I think it's a good way to avoid some common confusions. So let's go ahead and write out this multiplication. So we want to start by writing out the multiplication for the original matrix multiplication, or the quadratic form. Let's do that now. So we can think about this in a couple of ways. Why don't we start by finding that W transpose, since then we just multiplied that by X. Oops. And we'll just aim to find an element of W transpose. So let's just denote that J. So a jth element of W transpose, if we come back up here, let's copy this down. Maneuvering here. Sorry about this kind of infrastructural task here. Okay, so it equals this, but how can we write this out by maybe, or sorry, we're going to say it equals just this portion here. We'll kind of save this for now. Oh man, I thought I grabbed it. We'll save this for now. Oh man, sorry. This is probably not a better way for Notability to organize this, but I'm a little sloppy. Okay, so what we want to do is then figure out how we get one jth element of this. So the way we would do that is we first take, again, these dot products of basically this column and this row. So how could we write that out? Well, let's ignore the jth bit for a second and say, what's this particular dot product? Well, we match the first item in this vector with the first item in this vector, the second item in this vector, the second item in this vector, and so on. And so that means that what we're doing is we're saying take the sum from I equal 1 to n of xi and ai. Right, now we want to indicate the fact that this is only the jth component of W transpose because that gives the first component, right? So these things here give, in this case, this is the first component, W1, and then these things here give W2, and these things here give Wn. So how can we kind of represent this fact? Well, the way we could do it is to say, all right, well, there's also a J index that ranges over the columns of A. And that actually is also really helpful because note that in the end, let's actually keep moving this down, sorry. We are going to multiply this by this here. And so how can we, and note again that this formula here gives a 1 by n row vector. So then how can we write that out? Well, okay, so, this gives, 1 by n, gives an element of a 1 by n row vector, gives the jth element. So we would want to sum over j to get that row vector, but we can actually do something kind of nice, which is that we want to sum over j to get the row vector. But we can also index that by, or we can also use that to index that vector x, because note that each element in this row vector gets paired with, when we do the final multiplication, this here to form a dot product, right? So we can incorporate that information because these both have the same size. So we can say, okay, we want to go from j equals 1 to n. And then we also are going to be multiplying by xj. And this is the key to writing out correctly the derivative of this scalar product p, which is equal to this, by the way. So let's see how that works. And probably the best way to think about this double summation is to, again, let's clean up some of this stuff and test it out. And we're going to test it out by doing the following. We're going to fix a value of one of the indices and then vary over the other. Okay, so let's see how this works. So again, let's say that we're going to fix j equal to 1, let I vary from 1 to n, then sum. So how would we do that? Let's say that we're going to settle on j equal to 1. And so when we settle on j equal to 1, that means we pick the jth column. Here we'll do the first one. And then we do our dot product, right? Because this then says to vary from I equal to 1. I is the rows of this here and the columns of this here. And then just take the product of the i's or the xi and the ai, and then sum them up, which is the dot product. And then we are told to, okay, iterate that. And finally, we would also then take the product here as well. So we'll call this W1. And then we do this here. And then taking that product looks like this. And then ultimately, we would just sum over the different j's. So then we would say, okay, now we take the second j, We take the dot product. That gives W2. And we would then take, by the way, I should have made this clear. Oh, I did that down here, sorry. Here, and then we're summing these together, right? Which, I mean, makes sense because it's part of the dot product operation. I probably don't need to write it explicitly, but it makes it a little bit clearer. And then we do the same thing up through Wn. Oh, and I can again maybe just recognize the fact that I wrote this down here, xn, like that. And so then we're just summing over j. So we're taking this multiplication, and then we're taking this multiplication, then we're summing, and then we're summing, and then we're summing. So now what we want to do is partition this into the following. So we want to think about, okay, how would I come up with, say, a summation that can be written so that it involves for a given member of x, basically none of the x, one of the x terms, and then all of the x terms. And you'll see that that's why we refer to this as a quadratic form, because it looks a lot like your quadratic equation. So let's go ahead and write that out. So task and recall, so generally y is quadratic if y is equal to ax squared plus bx plus c. And so you can see here that there's one term that involves no x's, one term that involves just one x, and one that involves x squared, right? So we're going to see that we can actually do the same thing with this matrix, and I think it gives a nice way to understand a little bit more clearly what exactly is going on here. So let's come to that task now. So one way to think about this, let's copy down again kind of our matrix like this, would be to say let xk equal xn. And then we can think about doing the following. We want to try to understand how we could break up that matrix multiplication. So remember, this is a matrix multiplication that results in a scalar product, so we can actually go ahead and write out this entire thing just with summations. And we want to figure out, okay, how could we write this so that we partition out the terms that involve actually no xk's, in this case xn. And one way to see this is that if you think about it, when we did our matrix multiplication, we saw that we were using that row vector x transpose many different times. So I'm not going to write this out because I don't want to gunk up this matrix, or I won't write it out too much. But you saw that we kind of went here and we took that dot product, and that was the first element of W transpose. We came here, that was the second element, and so on. And then at the very end, we took the dot product of regular x with W transpose. So note that we used basically this matrix A only once. So we kind of exhausted it in a sense. And that's actually really helpful as a means of thinking about how we could represent this matrix multiplication in a way so that we make clear how we could, have some terms that involve no xn, some terms that involve just one xn, and then some terms that involve two xn's or xn squared. So let's write this out like this. So here's one way to think about it. We could, for instance, take this part of the row vector, which doesn't involve xn, and then take this part of the column A, A1, and then take the dot product of those things, which then forms basically one way to think about it is that you could write this kind of funny version of WT, so let's call it W tilde transpose. And what that would be is basically this. And let's let m equal n minus 1. So we sum over m like this, and we'll denote the jth element here like so. And then what we would do is say, okay, now we iterate over the j's, but we keep doing the same thing, right? Fundamentally. Now, we're not going to want to go to the last row. So why is that? Well, if we go to that last row, let's kind of show what would happen there. This should be an A. So if we go to that last row here and then take that dot product here, then what's going to happen is that when we do that, we're going to end up, this will be actually the nth element of W tilde, right? So note that we have n columns here. So taking the nth column with the vector x transpose or x tilde transpose, if you want to think about it, actually is going to produce that nth element, which would then force us to match that nth element in the row vector W transpose with this right here, which would include xn in the product. So we don't want to do that. So we're actually not going to do that. Oops. So we'll show what we use up here. And I'm not going to, since we can reuse this row vector, I'm not going to basically keep using that kind of green circling, because we'll just use that to indicate stuff we've used up in the matrix A. Okay, so we want to then iterate J also up to M as well. And so now I want you to think about how this generalizes. So we're picking this nice simple case where we can just stop the index short, but in general, this would also be equal to the following. Oh, and we need to put in our xj here as well. So this is just our same formula from before, except we stop the index short, basically going down the rows of A and then across the columns of A. So what this is equal to is also the following. So here we're just writing this more generically. So this would be true if we just simply don't have the case that j is equal to k and I is equal to k. I can show you sort of what that would look like. It's not quite as intuitive because we can't think about these kind of in these nice sort of like truncated matrix operations here. But what that would look like, let's say, for comparison, let xk equal x2. What that would look like, whoops, I have to do this here, is the following. Choose a new color here. So what that would mean is we would take these things here, and then we would skip right here, take these things here. So we take that dot product, right? Or again, it's a little kind of funny to call it a dot product because we're not able to make it a dot product of these shortened vectors. We actually kind of have to take it in two parts. But then we would do the same thing here. Whoops, don't grab that one. Here. And again, we're just kind of matching these with their corresponding parts. Now we would come all the way, in this case, oops. So for comparison, we can think about what that might look like for a different k. And then what that would look like is the following. We would take this kind of pseudo dot product here, taking all the elements but 2 here. Now we're also going to skip, in this case, the second column entirely. And the reason for that, again, is that would produce the second element of W transpose, which would then have to be matched with this, but we don't want any xk here. And then we would come all the way to the end and take these parts here. And again, kind of take this pseudo dot product. It's not as nice as the version that I was showing before with k equal to n, because then you can't write this as like a kind of truncated matrix algebra. And then what we would do is we would match these, right? So then we match this this first element here. We can write it like this sort of. So W tilde transpose in this case would be equal to basically, and then we'll kind of like mark this out. Actually, an X is not very clear. So we'll sort of like just conspicuously carve out that. And then we would basically be taking this dot product here at the end. Again, it's not really quite the same thing because, there's nothing here and there's nothing here. So we can't exactly write it as clearly, but that's the sort of basic idea. Okay, so now let's figure out how we could find all the terms that have exactly 1k involved in them. So we can do that now. But let's actually bring this down. And let's number these steps. So this will be step 2. And we'll say step 1. Okay. So we actually want to, I shouldn't have erased my nice things here. Okay, we'll do this like this. We want to kind of keep a running tally of the way that we've used up the matrix A, because that's a fine way to think about this, I think. So then we could think about, okay, well, how could we involve xn only once? So here's a way to do that. We could say, what if we take the parts of the dot product that we previously truncated, and so that was going by the way, the dot product I mean here is the columns of A and then the row vector X transpose. So that would be this here, this here. And then we're not going to touch this here, but we would go all the way to the end. And the reason, again, we won't touch this is that this would, in fact, produce that kind of nth element of the row vector x transpose, which would then need to be matched with this, which, again, can't happen. So we'll just pull this back. Okay, so we can think about it like this. We are going to go ahead and match all these things here, but note that these aren't actually going to get, as long as we don't use this here, we're going to end up producing a row vector that's got only m items in it, right? So we take these m columns right here. So we can do that now. And then what we would do, we would have a row vector that looks like this. We would have basically x, n, and we could have this kind of truncated matrix multiplication. And so how could we write this out? So how could we represent this as a summation? So let's first think about what we're actually doing here. We're not varying the ith component here at all because we're starting with the consistent row of A, and then we're matching that with the same element of x transpose, then we're just varying J. So we could write that out like this. We could say we're varying J from 1 up through M, and then we're summing over I equal to N, and N, I mean, that's a little silly, but that is what's happening here. And then we have xi, aij, xj. And so what this really means then is that we're not actually doing really much variation with that first index, or the inner index. So let's write it out like this, just for the sake of keeping things consistent with other notation you might see on the internet. So we're going to fix I equal to n, and let's use our standard notation here of k because n won't always be k. So we can just pull out that xk. We have the sum j equal to 1, and we'll write this as n and just say j not equal to k, which again is just generalizing to make this a little more abstract. And then we were setting I equal to k and then varying over j, like that. So that's how we write out this term here. And so now what we want to do is think about doing this in basically the same way, except we are going to focus on the xk that comes from the column vector x. So let's clean up our work a little bit here. Oh, but I didn't want to get rid of that. Okay, we're going to clean up our work slightly better. Okay, so now what we want to do is think about using these here, and note that these will be paired with these here, and what this will do is form basically that final element of W transpose. And again, we can kind of denote it with a tilde or some kind of indication that this is not exactly W transpose, but basically where these will go is here. Right, so we take that dot product and then that spits out. Again, it's a little bit hard, but you have to think about, so what component of the output is this? Well, we've got a 1 by n matrix multiplied by an n by n matrix, or 1 by n vector to be most exact. So we have our 1 by n vector by our n by n matrix. So taking the nth column of the matrix produces the nth column of the output here. So then we would multiply that. And now here, that's going to be matched with this here, right? Because, again, the dimensions have to agree. That's just how it works. So representing that, we could say, okay, what's going on in this case? Again, we'll kind of start with our nice notation for this specific example, and then I'll generalize it. So now here, whoops. Now here, we actually are varying once again I. And we're just going down to M. But what's going on with our J index here? Well, that's fixed at J equal to K. So we could write it out like this. Right, like that. And again, that's a very specific way of writing it that's only going to work if we have the situation where we can kind of avoid the fact of, or avoid using one element of some output by just adjusting the starting and ending point of the indices. So let's write that out more formally or more consistently. So here what we're doing is fixing J, so we can just factor it out and then varying over I. So let's factor out that xj, which again here will be xk, because n is k in this case. Then we sum over I to n, and again we just need to write that like this, so I not equal to k. Then we have x I a I like this. And here we are focusing on the kth column of a I. Okay, now finally we come to the very nice conclusion here, which is that there's really only one way to select the term with two x's in it. Which would be this, this, and this. And so what we're going to do is just write out what that would be. So that's this. In our case, it is a and n x n squared, or more generally, it is a k k x k squared. Okay, so now all we need to do is gather up these terms and then take the derivative. So let's kind of start assembling these things here, and I'll keep the more general form. So we'll have this one, and then this one, then we'll grab this one, and it is very long, but you'll see that this summarizes something pretty nice. And finally, we go grab the first one that we began with here. So all of that is equal to p. And then we want to take the derivative of p with respect to one of these items, right? Or with respect to this particular x. So we'll do that now. And how does that shake out? Well, so this here is just going to become 0 because there is no xk term involved. And then let's take an easy one. This here is just going to be the product rule, the chain rule. So we have here 2 a k k xk, just like that. And then what we need to do is deal with the interim terms. So we'll do that now. So we're going to bring down this here. And you can see that we are just going to, we only have one xk here possible. It's on the outside, so then we just have the summation of the inside. So that is this. And then this here, write this out here with a little more space. Again, it's just going to be, we basically are eliminating these here because we apply the power rule to them. Hopefully that part isn't too much trouble for people watching this. So we have I equal to 1, I not equal to k, to the n, xi, a, I, k. And so that is our derivative, and then we're just going to set that equal to 0. So we'll say, and let's write this out. Actually, we'll kind of grab these terms here and let's write this out more cleanly. So we'll do a little bit of a rearrangement here. Sorry, folks, I'm being very messy. So let's first get this all in black. And then we're just going to say, okay, now we want to set this equal to 0. All right, so then our next step is to come up with some kind of clever way of rewriting this. And there actually turns out to be a very clever way of rewriting this. So first of all, note that we've got this term here, and we want to see if we can maybe somehow find a way to cancel it. So if we look at this term here, this is saying go x, I, a, I, k for I equal to 1 up to n, but not for x equal to the k. Well, what would this term be if if I were equal to k? Well, we would then have a, k, k, x, k. So that's one of these terms here. And then you can see that the same is true here. So actually, what we can do is this nice, fun little thing here. Whoops. This gets super simple, as these things often seem to magically do in math. It's kind of a nice thing to remember, by the way, as many great proofs like this, you have to assume that the person who came up with it originally saw this in their head, saw where it was going to go, and then worked out the kind of gruesome details afterwards. So this just becomes this, because again, that last term has 2 times the term that is missing from each of the previous summations. So this is going to be our derivative, and then we just need to come up with a way of rewriting this that is clever, in a sense. Okay, so instead of actually going ahead and solving at this point, let's think about what these things represent, what these 2 summations represent, and then maybe we can actually come up with a formula for the derivative, not just with respect to one particular xk, but actually overall with respect to, say, the entire vector of variables here. So let's think about this for a second. And this one's actually going to be a little simpler here. So what does this formula tell us to do? Well, what this formula tells us to do is the following. It tells us we want to fix some particular column of A and then take the basically dot of that column with all of the values of x, or with x, right? And so a convenient way to represent that is like this. So here we just pick some k, some kth column, and then we take the dot product like this. So that's easy. And we've written that many times. But what does this represent here? You may want to pause and think about that for a moment, and I'll give you a second to do it. So the answer is that this represents taking some row of A and then dotting it with X, like so. And we could represent that in just this fashion here. So this is just going to be basically a subset of the following. Just like this. But what we may want to do is find a way to represent that as x transpose multiplied by something. And so kind of an interesting point here is we could write x transpose like this. And then what we want to do is actually just match this with, as noted before, the kth row of A. So what if instead we wrote this as A transpose, so now the kth row is the kth column, and then we just did that. And we're actually allowed to do that. So what we can do is say that this equals, right, the entire derivative, that is going to be equal to the following. Which is a pretty cool fact, I think, in fact. So what's our final step here? Well, we then want to think about what happens if we happen to have a situation where A is not only square, which means that it's n by n, but also symmetric. So then, of course, this just becomes x transpose by A, and then we just have this here. So we factor out the two. So this is a really cool fact, and we'll use this later on in the proof. So let's finish up the proof. So here our task is the following. We want to find the argmin, which means the argument that minimizes a particular function, in this case a loss function. So the argmin of beta here, and I'll denote this with a vector symbol for the first time, of our squared length of the vector u here, where u refers to the residual, and we define the residual in this way. And note here that I'm switching to the notation that's common in actual multivariate statistical analysis. So here x is not the vector of predictors or coefficients, sorry, but instead it's actually the design matrix or the matrix of predictors, right? So it's a matrix that's comprised of, say, things such as the following. So we might have education, income, something like the region in which one lives, so on and so forth. And then we have here person 1 to n. So that's what x represents in this case. Okay, so this is our task. Now, how will we go about doing this? So let's start by writing out what this actually means. So if we write out our function here, u, and we can actually just write out what u is briefly. So what is u? Well, what u is this. Now, if we try to find the squared length of u, first of all, note that u is just a vector, right? So we can find the length of it, this is sort of the Pythagorean theorem in n dimensions, by just dotting it with itself, or by writing it as a matrix multiplication, so the transpose of u, right multiplied by itself. So let's do that now. And from here on out, I'm going to just stick to writing vectors without any special notation, and I'll just use the double underscore to indicate this thing is a matrix. Okay. So let's write out the steps kind of as numbered steps. So what's our justification here? What this is the Pythagorean theorem. In Rn. And also equivalence of vector dotted with itself and transpose that vector. Whoops, I'm already breaking my promise to not use the vector notation, mostly just because it's tedious, so it's otherwise useful. Okay, so now let's go ahead and take step 2, which is going to be to distribute through that transpose operator in the first part. And so there's 2 steps here. First, we can just distribute a transpose, actually. But second, when we distribute the transpose to something that is a product, such as this here, we need to actually obey a different rule, and I'll explain that rule in a second. And so that rule is this. So first, transpose distributes. That's not the rule, actually. This is the rule. Oops. So what this tells us is that the transpose of a product is equal to the product of the inverted transposes. And let's think a little bit about why each of these rules actually makes a fair amount of sense. So first of all, if we think about this first rule here, that we can distribute the transpose, so this needs to make sense dimensionally. And so if we've got a row vector here, what that means is that if we're going to subtract something from it, it also needs to be a row vector. So we can think about what is beta transpose, x transpose, it's this. Oops, let's make this a beta. And let's write it like this, actually. Let's make it a little bit clearer. So this is a k by n matrix here. And this is a 1 by k vector here. And so we get, when we kind of all is said and done, we get a 1 by n row vector subtracted from a 1 by n row vector. So that checks out, right? That's just not a proof, but it's an intuition. Okay, and then the other point is this here. So what's an intuition for this point here? That AB transpose is equal to B transpose times A transpose. Again, this is not going to be a proof, it's just going to be an intuition. So let A have dimensions n by k, and B have dimensions k by p. Okay, so then the transpose, well, first of all, this has dimensions. Let's let this be equal to something, actually. Equal to p, which is in n by p. So p transpose is a member of p by n. So that means that AB transpose is in p by n. And so that means that if we distribute this transpose, the same needs to be true. So what that means is we've got B transpose, A transpose. So this is a member of P by K. This is K by N. And then we can see that this leads to a matrix in P by N. So that's some justification for that. Okay, cool. So we distribute that transpose, and that's really all we need to say about that. I'm not going to give a comprehensive proof. Okay, so let's write this out, and we may want to drag down what we had up here. Okay, so now let's distribute this. And this part is also a little bit tricky because it may not be clear why we're allowed to distribute here. One way to think about this is that if we just take this first bit here, this is a row vector minus a row vector. We just got a row vector back. And this is a column vector minus a column vector, and we just got a column vector back. And then implicitly, that means that this and this should be defined, and indeed they are, and this should be defined, and this should be defined. And then we can kind of just use our intuition that many, although not all, scalar algebra rules work in linear algebra. Okay, so we can distribute here. Okay, so we can say that this is by rules of the FOIL property in arbitrary dimension. Cool. Okay, so let's move on to step 4 here. Pardon me. And now we need to take a bit of a clever rewrite of some of these things that we have. So first, our point is this. We want to somehow show that a couple of these things are identical. And in particular, we want to show, that these things are identical here. So how might we do that? Well, first of all, note that what are the dimensions of these outputs? So each of these is a member of, let's write that out more concisely, the reals, which is pretty fascinating. So how is it that that works out? Well, let's look at this one here. So we have beta transpose, which is a 1 by k vector, times x transpose, which is a k by n vector, times y, which is an n by 1 vector. So these correspond and we're good, and we get a vector in 1 by n, and then a 1 by n vector times an n by 1 vector, of course, just gives a 1 by 1 scalar. And this one's even a little bit clearer. So we come down here, we've got a 1 by n vector times an n by k, times an n by k vector times a k by 1 vector, or n by k matrix, I should say. So let's take this one first. These cancel, we get an n by 1, and then these correspond, of course, and then we have a 1 by 1 scalar output as well. So that's pretty cool. And there's a couple of different ways of going about the proof from here. Let me actually try to motivate this, though, a little bit more clearly. So let's not use any kind of cheap tricks here, with no disrespect to the heroes from Rockford. So let's keep the pen right here, actually. So let's show what these things actually represent, right? So what does this represent? Well, so we've got beta transpose here, which is a vector of coefficients. So we have beta 1, beta 2, beta k, multiplied by a transpose matrix, right? So we've already seen this before. This is probably the best way to write this out. x1 transpose, x2 transpose, xk transpose. So then if we're thinking about what's happening here, well, we're taking basically these columns here, right, which represent basically for a particular person, their scores on all the variables, and multiplying through, right? So we say we are multiplying each I by the coefficients. And so then we do that successively for each person, right? So this is size n. So what that means is we have a 1 by n vector here. And what this represents is everyone's predicted value. And then what we do is we multiply that by this here. So this is y, This is an n by 1. Everyone's outcome. And really what this is y hat transpose y, if you really think about it. Okay, so then what is, let's move this over here. This here. So let's do the same kind of arithmetic, and let's take the right multiplication first. So we have x1, x2, xk, beta here. And what this gives us is this is again going to give us the same thing. I'll just call it y hat from the outset. And then this here is this. And this is y1, y2, yn. And this is the scalar transpose y hat. And of course, these things have to be the same. And so that means that we can actually equate these two things. And let's then go ahead and write out what those things are when we actually do go ahead and equate them. So we're going to make sure to show that not only are these equivalent, but they are also sort of effectively the same thing. So let's do that now. So how can we write this here? Just to show that they are in fact the same thing. This will take a little bit of doing, but let's think about it. Right, so what did this represent? So this, in this case, represented basically y transpose x beta. Oh, sorry, I'm looking at the wrong thing here. This represented that. Let's start with this one. Okay, so how would we do this? So we would say we sum from I equal to 1 over n. And we're thinking that we're going to basically go down the columns here, right? So how would we write that? Well, we're going down the columns and then basically taking that product with the left vector, the y transpose there, right? So we'd say that that's xij. And then we're going for the y's here, yi. And then we're going to go over to the betas, right? And so we also have our betas here. And then we need to, so again, the way to think about double summations is fix some value of j. So we'll pick the first column, and then we sum over j. Just like that. And what this tells us is that, like, let's say fix a particular column j. So we take the left product there over n. So we say yi xi1. And then what we're going to do at the very end of that is multiply by beta 1, and then we go down the columns. So again, what that looks like would be this. Here. And again, you can kind of see that this is going to be the same process as this. And then we would multiply by this. And so that is indeed this. And then we can verify that the same is true for our other multiplication here. So we've got beta transpose x transpose y, and let's write that out. And let's think about what's going on here. Let's zoom out a little bit. So we can say, okay, x transpose is going to be here basically dotted with y. And so we go down the y's. That's probably the easiest way to think about it when we do the linear combination approach. And we pair that with each of the xi's, which are here, actually our rows, or our columns, sorry, because it's x transpose. So we do that. and we think about fixing a particular row. So what this is telling us is pick some particular yi and then match it with all of the xi's and fix some value of j, which is here a row. So let's think about what that other matrix multiplication represents. So we'll take this and bring it down. Oops. And so what does this represent? Well, we've got x transpose right multiplied by y. So let's think about that for a second here. We'll do it like this. And then we've got, to the left-hand side there, there's a 1 by k vector of betas. Okay. So now if we think what's going on here, we can visualize this in one way as taking the rows of this matrix using a different matrix multiplication algorithm and then dotting those with y. And then what that'll do is give us basically this as our output. Just like that. So we get this column matrix or a vector here. And then we'll dot that with our vector of predictors. So if we think about what we really did here, it would be fair to say that we did this procedure here. Let's think about why. So if we think about it, we did iterate over the i's. So that was happening when we took this bit here. So that in this case represents going over xi because this is a transpose and multiplying by yi here. And we did that for a particular column, quote unquote, j, except here those are rows. And then we said for each, and we're going to again need to fix j. So for some one j, which would be this one here, then we multiply that by the jth predictor, which is this one here. And then we iterate, so we do this, then this, and that produces this product here, and then we do this. And indeed, that ends up being this summation here. So we're in good shape, and I know that's a lot, but let's go back up here and finally state what we meant to say with step 4 here. So we say, and this is actually really step 5. So step 4, we were just rewriting, let's say. So step 5, let's write this out separately. We say that this is equal to y transpose y minus 2y transpose this here plus okay, so now we're in good shape because remember that this is equal to u, right? Or in fact, it's equal to the squared length of u, I should say. And so then step 6, let's take the derivative of this function, and we could think about it as some particular function, but we would just write out the function as the squared length of u. So we'll just say the derivative of this thing with respect to beta, and let's just call it, let's say that we can just write this function here, g of u is this, whoops. So it's this. So let's think about all the different components here. So this just becomes 0, of course. And then this here, by a property that we proved before, this is pretty simple, right? So we just have beta times the matrix x, and so the beta goes away, and then we just have as the derivative basically that matrix x. And so we can just write that like this. Okay, we're in good shape. And finally, this part here is a little bit tricky, but remember that this is effectively a quadratic form. So let's let A denote this. And so then what is this? Well, then in that case, the derivative is this. And again, we just proved that a moment ago. Okay, so then what we want to do is set this equal to 0. And I'll write out why we did this. So and I know I'm kind of using a notation here that's slightly overlapping, but don't let that bother you too much. So let's set this equal to 0. So we say 0 is equal to, and the reason that we can do this is that this is the conditions for the argmin. Okay, so now we'll just do a little bit of basic algebra. And this part's actually a little silly because we can just even get rid of these here too. So our next step is then to just multiply on the right by the inverse of each. I'll write this in here. Make sure to put these in. So this is basic algebra. And this here is matrix algebra. Now, if these two things are equal, that means their transposes are equal. And so we can write this. And note here that this is going to get a little bit hinky, but we'll make some sense of it. And the rule here is this. Just like that. So that's justification enough. I think we don't need to go too deep into all the matrix properties here. And now let's just go ahead and sub some things in. Oh, and this, by the way, does not need to transpose here. And next we can do this, and we'll write out just substitution here. Now this part's kind of interesting here. So note that we've got x transpose x on our right hand side here, and that's going to be a k by k matrix, which is also symmetric. And so that means that the transpose of it is also equal to it. So we can just write this. And then finally, we are at the end of the proof here. And this is the ordinary least squares estimator. Thanks for watching.